Okay, so this is example 1.3. The question is to find the critical load in member AB, where A is pinned, B is rigid, and C is fixed. There are no axial shortening in member AB. Assume E and L to be equal in both members. Okay. So first off, this is a statically indeterminate structure, meaning that we have a redundancy of reaction forces. But we are going to do some tricks to solve this. So first off, I want to see how this frame will deflect. So if I draw a diagram, this is AB, this is BC. So we know that BC is rigid, meaning that there's a moment transfer in the joint. A, B, and C, and we have a load P there. So this part will buckle out like this, and this part will deflect somewhat like this. Something like this. It goes to 0 before it reaching the end point at C. Okay. That is how the frame will deflect. We know that we have some reaction forces. We have, let's call this NA. Let's call this for VA. And we have some moment here, MC. And we have a shear force, VC, and a normal force, NC there. Okay. Now, if I take the sum of the forces in the vertical direction, sum of the forces in the vertical direction equal to 0, we have NA minus P minus PC equals 0. And solve for NA, that is P plus VC. Now, here we can do a little trick. We know that there are no shortening in the member AB. So we can assume that VC is approximately 0, just because that the load P is so much bigger than VC. So VC will not contribute that much in the overall picture of the member AB. So since P is so much greater than VC, and VC will not contribute to the buckling of AB. The buckling of AB. And I can leave this as a homework for you to check if this is correct, this assumption. Or you can just trust me and just assume that's 0. Okay. So if we have, we can take the sum of the moments about B. This is the positive direction. This should be equal to 0. We can then solve for about P here, about B, I mean. We see that we have NA goes through point B, and VA has the arm L. And since we have a rigid point at B, and there is a moment transfer, we can safely assume that there has to be a moment in B as well. So VA, that's minus plus M should be equal to 0. So if you solve this for VA must then be equal to M over L. And to show that there has to be a moment there, we can draw a short, a little moment diagram of the frame. So we have AB there and BC here. And we know that in A, we don't have any moments because it's pin. In B, we have this load P. And in C, we have a moment MC and a shear force VC, which we said was 0. And we have a normal force NC there. Okay. So we know that there are no moments in A. But we know that there is a moment at B. It's a linear moment. Right? Because when VA travels up, it becomes more and more moments. So it's a moment on this side. And we know that in C, we have initially a moment there. And we could assume that this goes to 0. That doesn't make much sense. So it has to go down there. Because this part and this part has to be equal. This part and this part must be equal. There is a moment there that's equal to that moment. So that's why we can assume that there is some moment M at point B. You could cut this beam up as well. and you can solve for all the forces. I leave that up to you to do it however you like. So we have the solution for the VA force, that's M over L. Okay. If we now assume that VC was 0 because of there is no shortening of the column, then NA becomes just P. So we have solved the reaction forces at A. So we can cut up the beam, the column. So if we have NA here, which was equal to P. So here we have P, and here we have M over L. This will deflect, it will buckle, something like this. That's very exaggerated, but you get the point. We have a P here. We can cut the beam at some distance x, and this is some y. And we see that we have P here and M over L there. This is the cut at some distance x, and this is some distance y. And we have this P, internal force P, and we also have an internal moment, M of x, like this. Okay, so if we take the sum of the forces about this x, about this cut, the moment should be equal to 0, and we assume this is the positive. Is that we have M of x minus P times y minus M over L times x. This should be equal to 0. Solve this for M of x. So M of x is then equal to Py plus M over L times x. So now we have an expression for the moment. So we can use the moment for the curvature beam equation, which says that it's EI y prime prime is equal to minus M of x. Okay. Then we just get EI y prime is equal to minus Py minus M over L times. And if we just keep all the y's on one side and all the x on the other side, get EI y prime prime plus Py equals minus M over L times x. Okay. And if we let k squared equal to P over EI, we can divide everything by EI. So we have y prime prime plus k squared y equal to minus M over EIL times x. And this is the governing equation. Okay, so here we have a differential equation is a non-homogeneous differential equation, and we know how to solve this one. So y of x, that's the homogeneous solution, plus the particular solution, yp of x. And we know that yh of x, it's becoming pretty routine by now. That's a cosine ax plus b sine ax. Okay, so we see that the right-hand side of the governing equation is minus m over e I L times x. This is a polynomial. This is a constant times x. And we use our table to find out what the equivalent particular solution is. So yp of x is then equal to k1x plus k0. The first derivative of this is just k1. The second derivative of this is 0. We can insert this into the governing equation. Okay. The governing equation was y double prime plus k squared y equals minus m over e I L times x. So we get 0 plus k squared times k1x plus k0 equal minus m over e I L times x. If we divide by k squared, we get k1x plus k0 is equal to minus m over k squared e I L times x. But k squared, that is just p over ei. So ei cancels with ei, and we are left with m over pl times x. And we are using the method of undeterminate coefficients. So we compare the x terms. So k1 must equal to minus m over pl, and the constant term, so k0 must equal to, well, we have 0 constants on the right hand side. That's 0. So the particular solution then becomes minus m over pl times x. And now we can just insert this into the total solution. Is a cosine kx plus b sine kx minus m over pl times x. Okay. Now we can use our boundary conditions. So we know that in A, so this is we are assuming this is the x direction, this is the y direction in this case. So at x equals 0, we know there's no deflection. So at x equals 0, y of 0 is equal to 0. And in the task, it said that there assumed to be no foreshortening in the axial direction of this member AB. Then we can assume that at x equals L, y of L is also equal to 0. There is no deflection or shortening of the beam. at L. Okay, so y of 0 equals 0. That yields that A must equal 0. Okay, if you plug in L, it should be equal to 0. We get B sine KL minus M over P equals 0. We solve this for B, we get M over P times 1 over sine KL. Okay, easy enough. So our solution becomes B sine, that is just M over P, 1, we take sine KX over sine KL minus plus M over PL times X. M over PL times X. Can factor out M over P, and we get sine KX over sine KL minus X over L, like this. We need to take the derivative of this at some point. So the derivative becomes K cosine Kx over sine KL minus 1 over L. Okay. Now, if we look at the widget points in B, we know that there is a transference of moment. So let's take a closer look at the joint B. Let's look at joint B, rigid. Okay. So the joint B, it will deflect like this. So this is the column, this is the beam. So we know that the column will buckle like this, and the beam will deflect like this. So you can see that we have a slope here, or an angle, let's call that theta BC, and we have an angle here, let's call that theta BA. I call BA and BC because we are going from B to A down here. We're going from B to C there. That's why I denoted as B, C, and BA. Okay. So the trick here is to say that the angle BC has to be equal to the angle BA. Okay. And how do we find those angles? Well, we can start by looking at the member BC. Member BC. It doesn't matter which member you look at first. But since there are no shortening in the beam in the column AB, we can assume that in B it has to be a pin connection like this. This is B, this is C. And we have a moment here. Let's call that M. And we know that this will deflect something like this. Okay. And here we have the angle BC. Okay. We can use the slope deflection equation to find the angle. So using slope deflection equation, I write SDE. It's a very tedious process to write slope deflection equation. And remember that when this is star, when using SDE, remember clockwise rotation and moments are positive. To illustrate this, if I were to draw this diagram again, but it was in clockwise direction, the M would point this way and the slope would hold down like this. This is a positive, so theta BC. That is a positive rotation. This is just to illustrate what positive looks like. In our case, we have a counterclockwise moment and a counterclockwise rotation at BC. So we have in member BC that M is negative and theta BC is negative. Okay, so when you're using the SDE or slope deflection equation, which looks like this, Mij is equal to 2EI over L times 2 theta ij plus theta ji plus 3 psi plus FEMij. This is for positive clockwise. So for that rotation. Positive. Yeah. Since we have a counterclockwise moment and a counterclockwise angle. We need to add those in. So Mij, let's just figure this out. This is MBC, so 2EI over L times 2BC plus BCB theta CB plus 3 psi, chord rotation plus fixed end moments from B to C. Okay. We have no fixed moments from B to C. We have no chord rotation. We have no angle. The slope at C is 0. The BC, however, we have. That's what we want to calculate. But the moment BC, that is minus M, because we're going in the counterclockwise direction, 2EI over L times 2 BC. It's not positive, it's negative. It's going in the counterclockwise direction, minus BC. And the negative cancel each other out, so we get M equals to 4EI over L times theta BC. We solve this for the angle BC. We get ML over 4EI. EI. Okay. Now let's look at member AB. Okay. Member AB. We don't need to use slope deflection equations to solve this one. We have a moment there. So buckle like this. And we have an angle BA there. Here we can use conventional or traditional sign convention. And to reiterate what those are, we have I here and J there. And we have an angle here, theta IJ, and theta JI. The slope here and the slope there. This slope is negative. It's negative. And this slope is positive. So, like this. So we have a moment. So if we want to find theta ij, we have to take the account for the negative slopes, that is the minus dy dx for x equals 0, because we defined this angle to be positive, then you have to counteract the negative there. That's why it's negative. And theta ji is just dy dx inserted at x equals L. So we want to find theta BA in our column. And that is at x equals L, because this distance is L. So we are going to use this angle to find that. So angle BA is equal to dy dx inserted at x equals L. And we know that dy dx, that is m over p times k cosine kx over sine kl minus 1 over L. If we insert, I'll just write the derivative, insert L, this is then the angle BA. This then becomes m over p times k cosine kl over sine kl minus 1 over L. I want to factor out the k, so we get mk over p. Well, we know that k squared is equal to p over ei, so p becomes k squared ei. I just want to insert this for p. K squared ei times cosine divided by sine kl, that is just 1 over tangent kl, minus 1 over, well, I have an L down here, and I factor out the k. That means I have to divide by a k, kl. And we see that the k cancels, and we get m over ei. And I want to let u equal to kl, so I don't have to write that all the time. If I let u equals to kl, then k equals u over L. So k becomes u over L. So I put the L in the upstairs. Get 1 over tangent u minus 1 over u. This is theta BA. Okay. So I use the equation theta BC equal to theta BA. And we have m times L over 4 EI is equal to ML U EI times 1 over tangent U minus 1 over U. You see that M, the moment cancels. And also it sets that the length was the same and the material was the same. It didn't specify what I was. So we're going to assume that it's different. So we are left with, at the BC side, 1 over 4 times IBC equals 1 over U IBA times 1 over tangent U minus 1 over U. And I want to solve for tangent U. Okay. So if I multiply everything by U times IBA and then add 1 over u on both sides, we get 1 over tangent u is then equal to u IBA over 4 IBC plus 1 over u. Okay, I can put this on the same denominator. We get 1 over tangent u equals u times IBA plus 4 IBC divided by 4 u IBC. Okay. This should be a square, I think. Yeah, squared. Yeah, like this. And I can just take the inverse. So tangent u becomes 4 u IBC over u squared IBA plus 4 IBC. And this equation, this is called the stability condition equation. This is called the stability conditional equation. Or just the stability equation. Okay, so if we can play around with the second moment of area, so we can say that in case 1, if we let IBC equal to 0, what will happen? Well, the tangent of u just becomes 0. And we know that happens on if and only if u is equal to n times pi, where n equals 1, 2, 3, and so on. Okay. And we know that u is equal to KL, and we know that k squared is equal to n squared pi squared over L squared. So that k squared equals to p over ei. We can solve for p and get n squared pi squared ei over L squared. And if we let n equal 1, we get the critical load PCR equal to pi squared ei over L squared. This was if IBC was equal to 0. What that means in practicality is that the column, on top of the column, it's actually nothing. It has a secondary of moment equal to 0. So it's just this case, P, P. And we see that this is just the Euler buckling. Okay. In case 2, if IBC goes towards infinity, we get tangent U equals to 4U IBC over U squared IBA plus 4 IBC. Yeah. So the tangent U equals, that's the limit when IBC goes towards infinity. Then this just becomes on the numerator becomes infinity, and the denominator becomes also infinity. So we can use L'Hopital's rule. We can take the derivative of the numerator with respect to IBC. We get 4U. And we can take the derivative of the denominator with respect to IBC. And we get 4. Because this, take the derivative of this with respect to IBC, it becomes 0. So we're left with this. That means that the tangent U then becomes just U. Okay, this we can use a graphic calculator to solve. I'm going to use GeoGebra. You can use some other graphics calculator. We define f of u equal to tangent u and g of u equal to u. I want to find out where what is u when these two are equal. That happens there. For u equal to 4.4934. Okay. Take a screenshot of this. So that happens if u equal to 4.4934. Okay, and we know that u is KL. KL equals 4.4934. And we can use the same trick, k squared 4.4934 squared divided by L squared. And let k squared equal to P over EI. We can solve for the critical load. So P CR is then equal to 4.4934 squared EI over L squared. I want to factor out pi squared, just so I can easily compare the load later. So PCR is approximately equal then to 2.046 pi squared EI over L squared. Yeah, that was if IBC goes towards infinity. What that means in practicality is that you have the BC member is humongous, very large, so it's very stiff. And obviously, you will have a lot of force. So IBC goes to infinity. So this P has to be really big to be able to buckle this member down here. Okay. Let's look at case number 3. If IBC equals to IBA, let's just call that I. Then we have that tangent U is equal to, what was it again? 4U for UI, for UI divided by U squared I plus 4I. Let's double check if that's correct. Yes. So the I cancels. So the tangent U is then equal to 4U over U squared plus 4. And again, we can use a calculator to solve this. Just delete the previous. F of U equal tangent U. G of U equals 4U divided by U squared plus 4. And we want to find out where these two are equal. That happens if U is equal to 3.8289. This. So if U is equal to 3. What did I say? 8. You put 8289. 8289. 8289. Okay, and again, we know that KL is equal to 3.8289. Square both sides and divide by L squared. K squared is equal to 3.8289 squared divided by L squared. And we let K squared equal to P over EI and solve for P. The critical load P is then equal to 3.8289 squared EI over L squared. And again, factor out pi squared. And I get the critical load is then equal to 1.485, if I'm not mistaken. 1.485 pi squared EI over L squared. That was IBC equal to IBA. Okay, so if we just compare the critical loads, so if IBC is equal to 0, we have the Euler buckling, and if IBC was equal to IBA, the factor was 1.485, and if IBC tended towards infinity, we get 2.046. Yeah. So that was example 3.1.